Okay, so let's begin lecture 17, week 7, the Monte Carlo method. This is part of the course NE402, Intermediate Nuclear Engineering, Diffusion and Transport of Radiation and Monte Carlo Simulation. Now, in lectures 15 and 16, I went through the basics of random processes, random variables, probability and statistics, central limit theorem, the law of large numbers, Chebyshev inequality, and how to sample from continuous and non-analytic PDFs. So those two lectures are the prerequisite for this lecture. So in case you haven't heard lectures 15 and 16, before this lecture, please go through 15 and 16. Well, that's my name, my number, personal email, official email, and personal website. As I always say before, you're welcome to send suggestions, ask questions, and any feedback would help me in improving these lectures. Okay, so let's begin with the Monte Carlo method. Now, this method we are going to discuss in the context of the simulation of neutrons and photons. We're going to see how we can carry out a simulation as they begin their life as source particles to ultimately end their life by their death, by which we mean that they're absorbed or they leak out from the system. Now, there are many good books that you can consult side by side with these lectures and with this book, which is going to be out probably in about 6 months. So these lectures are taken from this book, which covers all the three techniques and their applications. So the books that I would say that in addition to this you can go through are by Dunn and Schultes, Kalos and Whitlock, 2008, McLaren, 2018. Now the older ones which I studied from as a student were Hammersley and Hanscom, 1964. I don't know if that's available now, but I used to read them in Madison and at Cambridge. That's a very old but useful book. Then Spanier and Gelbard. I met Dr. Gelbard at a conference in Hungary, in Budapest. I think it was 1989 or 90. His book is also a very good but slightly difficult way of understanding Monte Carlo simulation. Bell and Gladstone do not cover this in great detail, but there's just a very little bit of material on Monte Carlo methods. Then, of course, you can look through the lectures from Los Alamos, very good lectures by Forrest Brown and very good papers out of many workers, especially Los Alamos, Tom Booth, and Forrest Brown, and Kedirovsky, and a number of very good papers I've seen from Los Alamos. So what I would tell you is that the Monte Carlo method that I'm talking about does not involve the solution of any equation, but you can interpret it to follow the integral form of the transport equation, where I took you through a derivation starting from the integral differential equation. We also considered the method of characteristics, where you convert the PDE into an ODE. And then in terms of the collision density in phase space P, I wrote it as a direct contribution plus as an indirect contribution. So I would like you to think of it in terms of the collision density form, that chi of P is S of P plus chi of P prime integrated over D prime multiplied by the scattering kernel K coming from P prime to P and integrated over all P primes. So that's the best picture that I can think of. Okay, historically the name Monte Carlo was given by Metropolis of the Theoretical Physics Division of the Manhattan Project in 1942. according to this reference. And then Metropolis and ullah 1949 used it extensively. They began, these were the early days of Monte Carlo simulation. And the group included Teller. Von Neumann came up with a fantastic convergence series, which we will use a lot in Monte Carlo simulation. Ulam and Richtmeier. Richtmeier's name I always associate with hydrodynamics and implosion. Now, remember that those were the days when they had mechanical computing and electrical computing. So electronics was not there. And so these computers were used, and it is said that Enrico Fermi used the statistical sampling technique even further back in 1934 when he was working on neutron diffusion in Rome. Now, in 1944, the development of the atomic bomb project, the Manhattan Project, entered its final phase. And you know that in 1945, 2 nuclear weapons were dropped over Japan, one at Hiroshima and one at Nagasaki. So the 3 problems at the center of the nuclear weapons program at Los Alamos were neutron transport, the behavior of materials under very high temperatures and pressures, and fluid dynamics. And these all required mathematical computation for the design and prediction of the yield from the nuclear weapons. Now, after the nuclear weapons program, then nuclear engineering came into submarine reactors and then into civil power reactors. And as I said, we've got over 440 nuclear power reactors operating in the world at the moment. Now, several mathematical methods were developed along with computing hardware that led to the 2 earth-shaking events of 1945. The successful test at Alamo Gordo, I hope I pronounce it right, and the building of the first electronic computer. So the nuclear and the electronics advancements were a great step for science and technology. Now, since the 1940s, at that time, I'm sure people thought that Monte Carlo methods would not really develop to the extent that we have them now. Even when I was an undergraduate student at Queen Mary College, we did not have laptops, and the university, Queen Mary College, just had one mainframe computer, and we could not even imagine that someday we would have laptops. So anyway, so now with all this that you see these days, such powerful computing available with all of us. So you see that Monte Carlo methods have found a very strong place in many areas of science and engineering. And I'm sure that as time passes and 10 years from now, probably when you have optical computing, then Monte Carlo methods will become more and more attractive. And they've gone from science and engineering into medicine, forecasting, in finance, and weather prediction, and God knows what. So let me start with something familiar to all of us. It's the evaluation of integrals. Now you might think that why are we doing the Monte Carlo method for a deterministic problem? But let's start with a stochastic method, which is actually designed for random processes. And let's use it to solve a deterministic problem like 3 plus 2. So let's start first of all with the Monte Carlo evaluation of integrals. Now, the MC method of estimating integrals is carried out by sampling for the mean of the function or by a simulation called the hit and miss procedure, where we see how many have come in the domain of interest and how many have not come in the domain of interest. Now, in its easiest form, a one-dimensional integral can be written as the integral I equal to f of x dx between a and b. Now, if you can take this f outside the integral and write it as f inside these angular brackets, then all that you've left inside is dx. And dx integrated between a and b is just b minus a. So here's a very simplistic way of thinking what the integral of a function is. So you can say I is the answer is I equal to the mean value of f multiplied by the width of the interval. Now, how do you get the mean value of f? Well, you can just sample different values of x and get the value of the function at those values of x and sum them up from I equal 1 to n, whether you've got 100 or 1,000 or 10,000 or a million sampling points that you've got, divided by n. So this is the arithmetic average. And you can say that the integral is now, I haven't written an equal sign, but an equal with a curly thing up there. So it's almost equal to b minus a times what we estimate the mean value of f to be. Well, is that good? Is that bad? That we'll talk about later, but it's a way of evaluating an integral. Now, of course, if you have a simple integral, then there's no point doing that because there are better methods to do that. And the best method I can think of is Gaussian quadrature, which we also discussed in transport theory using the SN. So the SN method, the discrete ordinates method, can use a finite number of angles to discretize the transport equation and then solve it numerically by getting ax equal to b, the standard ax equal to b. Okay, so then when would Monte Carlo be an attractive option for carrying out integral evaluation? So this is one possibility. If you're solving a multi-dimensional integral, so you've got 1, 2, n dimensions, and you've got a function of x1, x2, x3, all the way up to xn. So now you see the problem has become really big. And so all the other techniques that you can imagine would really become so huge that they might not be attractive anymore. So then this would be good that you can again get the mean values over all the dimensions and express it like b1 minus a1 over n multiplied by n of these and do the sampling of the vector xi and obtain the mean value and estimate the integral. The total number of points that you've got is now a product because of the number of dimensions. It's a product of ni that you take in each dimension, so that the integral takes the same form as for the 1D case. Now it is easy to say that the mean value of the function is required only once by sampling a single point, which is the vector x for the ith evaluation. Thus, if you had a 5-dimensional function, a 5-dimensional integral with 1,000 points in each dimension, so 10 to the 3 times 10 to the 5, 10 to the 15 evaluations. So imagine what a huge computation that would be. So this is where Monte Carlo estimation with possibly 1,000 or 1 million would be able to get you a reasonable good answer. So when the function is difficult, such as the one which I'm going to show you below, then a hit and miss technique is useful. A point is generated randomly, and the ratio of the number of hits nh to the total number of trials n determines the area under the curve. So if your function looks something like this, then what can you see over here? That this is the important area, this is the important area, but this is not the important area. So you can draw a bounding rectangle above it, and this is what we discussed when we saw how to sample from non-analytic functions. So this is the hit and miss technique. Now let's see some examples. Now exercise 5.1, let's do this. So let me show you this integral x squared plus y squared plus 3x plus 2y. Okay, so this is what it looks like in MATLAB. Let me make it a little bit smaller. Okay, so this is what it looks like on MATLAB, and I plotted this function. So it's this thing. Now, if you want to compute the area under this function between a1 and a2 on the x-axis and b1, a1, a2 and b2 on the y-axis, then this is a two-dimensional integral, and we need to find the mean value of this function. See what a function it is. So, and of course, I cannot plot anything higher than this. Of higher, I cannot show you something of fx, y, z. I cannot show you that because I don't know how to plot the fourth axis. So beyond three variables, beyond three independent variables, there's no way we can plot it. So that's where MC becomes very useful. So you can do this yourself. That's an exercise for you. And here's another exercise for you where this could be something useful. So here is the sine r over r function. Okay, now look at this. At the center, it goes up and then comes down over here at the edges, then goes up a little bit and comes down. So this is the projection of all these are circles, x squared plus y squared on the xy plane. So do this yourself and you'll see that you get some estimate. Now, Monte Carlo problems, just as I told you for transport problems, that it's better to start in terms of benchmarks. Now, I would suggest the same thing when you're doing integral evaluation, that do it for something for which the exact solution is known. Okay, now let's come to importance sampling. So I told you in the last lecture, lecture 16, that a Monte Carlo result has to be good. Now the word good means that it should be accurate and it should be precise. The word accurate in Monte Carlo simulation is associated with the expectation value of the mean. So the expectation value of the mean of the sample should be good, should be a good representation of the expectation value of the mean of the population. Okay, so that is what we mean by accurate. For example, if the average age is 32 of a huge population, right, of 10 million people, and you carry out a simulation and you say the average age is 10, so that's called an inaccurate estimate, because no matter how many samples you took, you got a bad result. So an accurate simulation should be one which gives the correct mean. So the sample mean should be very close to the population mean, and that's what we call an accurate answer. Then there is precision of a Monte Carlo result. Precision, the word precision in Monte Carlo is associated with standard deviation, variance, or the spread of your results. So the spread should be small, and that is what we mean by a precise answer. So an accurate and precise answer is called a good Monte Carlo estimate. Now, an answer can be inaccurate and precise. It can be accurate and not precise. So there are two possibilities here and two possibilities here. So out of four possibilities, the answer that you want, what we're going to call a good answer, has got to be accurate and it's got to be precise. So one of our goals is to reduce the variance of our estimate. And when we reduce the variance of our estimate, we talk of importance sampling. Importance sampling in the sense of the adjoint function is also correct, which I introduced very early to you. I said there's something called the adjoint flux, and just as there's called the forward or the flux, when we don't say anything, we mean the forward flux. So I told you that there's a phi plus, which we call the adjoint flux, and that is the importance function. Okay, so the importance sampling is something where people want to reduce the variance and increase the precision. The accuracy is kind of guaranteed by the law of large numbers, which we discussed in lecture 15 and 16. Lectures 15 and 16. The law of large numbers comes out of the central limit theorem, and please go through it again if you have not understood that, because need to understand that the sample variance of the mean is actually the population variance divided by the n, where n is the population you consider, the number of points that you sample. So let's try to do an exercise where we reduce the variance of our estimate. And accuracy, let's say, is okay. So ideally, what is the best variance that you think we should be able to get? The best variance that we should be able to, that we should think of trying to achieve is 0. Or if you cannot achieve a variance of 0, then it should be some very small number. Now the question is that, is it possible to obtain a 0 variance? That's going to be our objective. So our objective is going to be to carry out a simulation with 0 variance, which means that every time you get an estimate, for example, 5.4368, then every time it should be 5.4368, whether you do 1,000 simulations or 1,000,000 simulations. If you always get 5.4368, then the variance will be 0. And then I'll go and say that my answer is 5.4368. And then if anybody says, what's the variance, what's the standard deviation, I'll say there's no standard deviation. So they'll say that means you've got a deterministic answer. And I'll say, yes, I carried out a Monte Carlo simulation and I got an accurate and a precise answer. So I got an answer with 0 variance. Is it possible? So let's see if it's possible or not. Now, first of all, let's see that how can we improve the variance. So one of the ways that variance can be reduced is by a technique known as importance sampling, i.e. giving more importance to numbers that are more important. And that's what I told you when we looked at the exponential PDF. I said that e to the minus x gives more importance to the small numbers and less importance to the big numbers, as opposed to a uniform random number, which gives equal importance to small and big numbers. So let's see that how can we give more importance to numbers that have a high associated probability, and conversely, how can we give less importance to numbers which have a low associated probability. So the MC method of estimating integrals is now carried out by sampling for the mean of the function or the hit and miss procedure. So if we had to sample f of x, I'm just going to ask you now to divide it by some function g. But if you divide by some function g, then you've got to multiply also by the same function g, so that your original problem is not disturbed. So the integral I equal to f of x dx is now looked at as f of f over g times g. So if I say that I'm going to carry out a sampling from g, I'm going to use g of x over here. So there's a g of x missing over here. So if I say that I'm going to use g of x as a PDF to sample x from, then I can take out the mean value of f over g. And g of x dx between a and b is then understood to be 1. Okay, so there is a g of x over here. Okay, so here you should write g of x, and here you should multiply by a g bar also. Okay, so what is the estimator? Now the estimator, whenever we have a function multiplying by a PDF, so we call it an estimator. So let me give the symbol small h of x to the estimator, which is f of x, our actual function, divided by g of x, which is an importance function that I'm going to introduce over here. Now, it can be shown that by a suitable choice of the importance function g of x, this process would lead to a 0 variance solution. It is possible. And that g of x would then be related to the adjoint function. Okay, so before we come to the broad generalizations, let's look at a simple example. So let me consider that I want to carry out this evaluation, that I is equal to e to the minus x dx. Now, do you know the answer to this? Yes, because the answer is, if I put e to the minus x, the integral of this is e to the minus x with the minus sign. And when you evaluate it between 0 and 1, you get 1 minus e to the minus 1. So e is 2.71828. So you know what is e to the minus 1. So the answer we know that is 1 minus 1 over e. Now let's pretend that we didn't know the answer. Now if you don't know the answer and this is the integral you want to do, so let me use this PDF. Let me use this function g. Now let me use this function g as a PDF. Now do you agree, first of all, that this is a PDF? Do you agree that 5.6 is a PDF? Well, when I was going through the lecture on PDF and CDF, I said that I always tell my students that if I tell you that this is a PDF, then you've got to integrate this between the limits, and you have got to convince yourself that the answer is 1. Because if g of x dx integrated between 0 and 1 is not 1, then it is not a legitimate PDF. So you can satisfy yourself that yes, the g of x that I'm giving you is actually a legitimate PDF. Okay, so this leads to I is equal to between 0 and 1, e to the x. Again, I should have put 1 minus e to the minus 1 outside over here. Now, because if you divide by 1 minus e to the minus 1, you must also multiply by 1 minus e to the minus 1 inside here. And you can see that's just a number, so I can take it out. So there's no such thing as the mean of 1 minus 1 over e. So I know 1 minus 1 over e. So whatever you sample inside this makes no difference on the estimator. So the estimator is always 1 minus 1 over e. And so I get the answer of this as 1 minus 1 over e with a 0 variance. Okay, now it was a coincidence that the problem matched a PDF, which was analytical. It was a coincidence. But that's not always the case. It's not always the case that you get such a nice and simple question. So what did I actually do? So while it was easy for me to demonstrate a 0 variance result for you for this simple problem, I sort of knew what the answer was. So I knew a priori from before that what was the answer. So if you know, so to generalize this in English is that if you know what the answer is, you can get a 0 variance solution. Now that doesn't make a lot of sense, because if you know what the answer is, why would you want to find the answer? So, so one case where you can give a 0 variance solution is where you know the answer a priori, which is not always possible. So what I would say to you that if you do not know the answer of the thing, then you can use an importance function which looks like the function f of x. And for example, if f of x was 3x squared plus 4x cubed all multiplied by e to the minus x. So I'd say that take x e to the minus x as your PDF and normalize it, sample from there, and then solve the problem. And I assure you that you'd get a better result with less computational effort. So that would be something where the variance would be reduced. So the importance function is very useful in reducing the variance. And in the best of all circumstances, you can obtain a 0 variance solution. So that's a very good research topic. And in fact, it really has been. And people like Tom Booth, and I've seen very good papers by many authors on variance reduction. So variance reduction in Monte Carlo simulation in nuclear engineering has been and still is a great research topic. So importance function is something that you should try to get and use and bias your simulation with the importance function to make your simulation more efficient computationally. And the answer to that is that you should use the adjoint function. Now, this brings us to saying that do you have a knowledge of the adjoint function? The answer to that question is that yes, you do have a knowledge of the adjoint function. And just like you saw that the way we can solve the forward transport equation or the forward diffusion equation, there's a way that you can also solve the adjoint transport equation numerically or the adjoint diffusion equation either numerically or analytically for a simple case. So again, here's a PhD. A PhD topic is that you are given a problem in regular or irregular geometry. For example, a tokamak, or something like a stellarator, or something which is a shield of a reactor, or something which is a Gen 4 reactor with a lot of asymmetry. So in this day and age, when you're solving fission and fusion problems of relevance to today, so in your problem, solve the transport equation backwards and get the adjoint function and use that adjoint function as a Lagrange multiplier, either in the Lagrangian deterministic formulation or in the Monte Carlo simulation as a biasing function. You see, I've said so much in all this, but gradually, we'll come to this because till here it can be a BS at an MS level course also. So when you go beyond the MS level in PhD or in research, so that's very important that you be able to get your adjoint flux, which is your importance function, and follow one of the two paths which I mentioned, i.e. the deterministic path where you write the Lagrangian as a sum of your performance index plus the Lagrange multiplier multiplied by your constraint condition, which is the transport equation. So there you use the adjoint function as your Lagrange multiplier, as the importance function, and numerically optimize, obtain the best distribution of material, whatever you're trying to do, and that's a wonderful design optimization. So if you do that in the deterministic sense, excellent. If you can do that in the stochastic sense, then excellent also. And that is what today's nuclear engineering design is all about, of optimizing, of making the best possible use of your resources. For example, in the ITER experiment, International Thermonuclear Experimental Reactor, if they're using D plus T, deuterium and tritium, then to produce neutron plus lithium and 17.6 MeV. So the 14 MeV neutron would go into the blanket. So if you place lithium, like lithium oxide or any other mixture of lithium in the blanket, so then you can breed your fuel N plus Li, Li36 and Li37, the two isotopes of lithium. You can breed tritium. Now, tritium does not occur in nature. So there's another very good idea for a PhD or for research, that in ITER, design an optimal blanket using this adjoint function. And if you do Monte Carlo simulation with the adjoint function, you'll get an excellent answer for a design of a blanket to produce fuel. Just like breeding plutonium in a nuclear fission reactor is such an important thing, so breeding tritium in a fusion reactor is an equally important thing. Okay, now having said that, let me now come to the MC solution of integral equations. So let's go back to our previous lecture where we wrote down the multi-group, meaning the G superscript for energy group. So the phase space of interest was R E omega t. The E I've dropped here out of here and put a discretized index G representing the group energy group E, EG. So inside this, the collision density chi is expressed as a direct contribution from the source plus an indirect contribution from the collision density at some other energy G prime, which has been transported, which has collided and come into R G omega t. So let's look at this process. So this is the scattering kernel written k, where k is written separately as a c times a t. First the transport takes place, then the collision takes place, which changes the energy and the angle. So this is a perfect depiction of what is happening in nature. So the collision operator C hat and the transport operator T hat are defined in, in a previous lecture. This in terms of sigma S over sigma, and this in terms of e to the minus sigma t multiplied by sigma t ds. So if you go to that lecture and see the explicit forms for the collision operator and the transport operator, then you'll see that this is so analytical and so intuitive that it's sitting there naturally to carry out an MC simulation. So what we need to decide is that what are the tallies, the scores that we would like to have. So I'm going to talk to you about tallies, because what is it we're trying to get? The flux. You're trying to get the flux or the current. The flux is that how many neutrons per centimeter square per second are there? How many photons per centimeter square per second are there? Because if you know how many per centimeter square per second there are of anything, then you can multiply it by some macroscopic cross-section and you can get some reaction of interest that you're looking for, such as the number of fissions, such as the number of scatterings, such as the number of tritium atoms being bred, such as the number of plutonium-239 atoms being bred in the breeder of a fast reactor. So everything depends on the flux. So everything in a Monte Carlo simulation depends on a tally. And the tally is the thing that you're trying to score in a bank. You're trying to accumulate your score, and so that when you've completed your simulation, you obtain the arithmetic average, and then the law of large number tells us that the answer you get will represent the population. And how good or how bad it will be depends on the way the mean value depicts the mean of the population, as well as having a small variance. So you want a small variance and you want a good estimate of the tally. So these are the two things that we're going to study in the next lecture. So I'll stop over here, leave you with this formulation. So today we talked about Monte Carlo method, how it's used to evaluate integrals. Then we looked at variance reduction, and we just touched on variance reduction, the concept. And now I was talking to you about Monte Carlo solution of a stochastic process, of a random process. So two things I introduced to you in this lecture: the use of a stochastic method to solve a deterministic problem, and then the use of a stochastic method to solve a stochastic problem. Okay, so these are two distinct and separate areas. And I also told you that you could use the importance function in a Lagrangian deterministic formulation, as well as a biasing function for a Monte Carlo simulation. So that is the crux of a nuclear system design, optimization. So first of all, design a thing, and then second, first target, be able to design something, be able to get a tally. Second objective, to make the best design. The best design means the an optimal design. It's got to be an optimal design. If you do not design in an optimal way, then of course, that's not what engineering is all about. Engineering is about having the best possible design. Okay, and I'll come to that at the end of this lecture. So I think we'll stop over here with this one sentence, that the MC process, which can be understood to be a simulation of the integral formulation, is also known as a Neumann series solution, and this we'll talk about in more detail. So I wish I could ask you questions, but let's reserve all that till the end of the lecture, when we'll have lots and lots of exercises where we can practice whatever we learn. Okay. So